Josh, I think, has already told you all the history of your association with this project.
Not yet.
Oh, okay.
I was waiting for everyone to be here, for the people that already know, I guess.
So, yeah, do you want to say something?
Oh, whatever.
I was going to introduce you to that.
Oh.
So Josh is a former solar REU student from SAO. He at that time he used to go to school at the infamous New College of Florida.
Was it infamous at the time?
It wasn't. And currently, I mean, he's working with Bernard Klingenberg, his undergraduate advisor, who was actually at Williams at that time, but is now at New College. And he is now working with Anne Lee at the Carnegie Mellon University as a PhD student in statistics. And in the solar REU project, he started working with me on flare distribution modeling. And I said, well, it's all easy. You just measure the power law slope and figure out what the uncertainty is using Bootstrap. And Josh was I was very frustrated with what he was doing, because he said, it just cannot be done. And I said, no, of course it can be done. And he said, no. And anyway, so this whole thing that he's going to be talking about is why it is not possible to do that. So take it away, Josh.
Yeah, I'll thank you for the introduction. And as Vinay mentioned, yeah, I'm started off with the solar REU, and I have now found myself 5-6 years later at Carnegie Mellon in the Stats PhD program. I'm also part of the STAMPS Research Center, which some of you might have already heard this, but it's the statistical methods for the physical sciences based at CMU. So it's a collaboration between our stats department and similar to CHASC, except a little bit more broad, not just astronomy, but lots of really any of the physical sciences from, we do anything from weather prediction to high energy astrophysics, high energy physics. So yeah, I'm excited to be here. And yeah, this presentation and the results here that I'll present kind of started off from questioning an assumption we were making when we were doing Bootstrap to get some error bars around some of our estimates. And it turned into a long and winding road or path. And I think we finally find ourselves at least with some pretty solid conclusions. So I'll jump right into that. So from the title, maybe a little provocative, but solar flare statistics don't follow Poisson necessarily. And one of the causes that I will try to argue is the result, this overdispersion is the result of overlapping active regions. And I want to thank, of course, my collaborators, Vinay, Bernard Klingenberg, who is my undergraduate and master's advisor at New College of Florida, and Xiao Li. We have put a lot of time into this project, and I could not have come to get any of these results without their support over the years. So just what to expect. I'll spend a little bit of the beginning doing a quick refresher on self-organized criticality, the Poisson process, how these are related, and then, of course, to solar flares, which is here what we're here to talk about. And then I'm going to present to you 3 key takeaways or results from our analysis. So the first is that aggregate flare count distributions are overdispersed relative to the Poisson distribution. Next, if you look at the waiting time distributions of flares within individual active regions, these actually depart from the exponential distribution and are themselves overdispersed. And 3, in modeling the observed counting process, which you can think of this as a mixture of temporally overlapping active regions, we do observe theoretically overdispersion, and I'll explain that more. And then moving forward, I'll kind of give you an overview of the implications for future flare studies, and then hopefully what we'll wrap up soon for our future work. And this is taking this to be quite casual, so if anybody has questions, please let me know as we're going through the slides. So first off, on the background, what I mentioned, we'll talk about SOC and the Poisson process very quickly. So some of the key models right now for flares are based on what we call self-organized criticality, or SOC processes. So intuitively, I just like to think of this as avalanches. So you have some energy buildup and you can have small perturbations in the system, and this will trigger cascading events. So they reach at some point, as energy is put into the system, reach some instability threshold. And then you have, in the case of avalanches in a sand pile, it reaches some threshold, and then you have a large avalanche. So some release of energy from the system. With relation to flares, your solar kernel will evolve to some critical state where the flares release their energy at various scales. So they're kind of scale invariant. And so some of these key properties based on the SOC model that we would, what we expect under the SOC models are: one, their energies follow power law. So you can just see the equation. So they're proportional to the energy to the negative alpha. So alpha is our power law parameter, the slope of the power law. If you look at this in log space, you would expect to have, so log counts to log energies, you'd expect a linear relationship. And then with respect to the flare occurrences, these we would expect under certain SOC models to follow a Poisson process. So if it's stationary, you'd expect the counts to follow Poisson distribution, which have certain properties that we can check for. And then the waiting times, so the times between flares would be distributed as exponential, which also has certain desired properties that we'll need to check for. And so I just, as a quick visualization, the figures on the right side in panel A, I just plotted over the years from solar cycle 23 and 24, the flare total energies that we observe. So each point is a flare. The color corresponds to the flare classification. So based on the peak flux, and then the energies on the y-axis, and then our year. And you can see roughly the solar cycle, but we have something interesting going on there, which I'll discuss later. But you see, we observe higher frequency near the solar maximum, near the peak, and larger flares in general. So there's some changing, this is non-stationary, there's some changing frequency of flares, both by their classification and intensities. And then you just see a histogram on the right side of the peak fluxes for these flaring events. And so those, we could look at those distributions, and we would expect on these models them to follow, for example, the energies of power law. And then bringing me to the count or the occurrences, we can think about the flare occurrences as a stationary Poisson process. So just to keep it pretty simple, I'll go over this quickly. So under a stationary Poisson process, this is a special case of a counting process where you have the properties that any disjoint intervals, time intervals, are independent. And then it's a stationary Poisson process, so your rate, so the rate of occurrence of events, is fixed. So some lambda, think of this as flares per hour or flares for some time interval, that's fixed over an interval. And then through this, the distribution of counts would be Poisson distributed. And the key property here is that under the Poisson distribution or Poisson process, the event counts, their expected value will be equal to the variance. So the expected value for some fixed interval would be lambda, and then you'd also expect that the variance to be equal to that as well. And this is very common assumption made in solar and stellar flare studies, that the counts are often assumed to be Poisson distributed. You can get some uncertainty quantification based on this assumption. So it's important to check this. And then really briefly, this relates to the waiting times. So if you actually take the difference between the two consecutive events, you get the waiting times between those events, and you'd expect those to follow exponential or an exponential distribution. And this has the memorylessness property in addition to that you would actually expect the expected value of the waiting times is equal to the standard deviation as well. So these have some properties that we need to check before we make these assumptions. And I'll briefly introduce this for context. So we also have what we call a non-stationary Poisson process. And you can kind of check this by checking whether you have overdispersion. So we'll define overdispersion as when your variance is greater than your expected value with respect to the Poisson distribution. So if you expect to have a Poisson distribution, your variance should be equal to your mean count. And if you have that the variance is larger than the mean under the Poisson relative to Poisson, that's over dispersion. Of course, if it's less than, that's under dispersion. We could also check this with the exponential distribution. So if your standard deviation is greater than the mean, that's over dispersed relative to the exponential distribution. This over dispersion can be caused by non-stationarity. So you might have a time varying rate parameter. So if I look at the number of events at a given time or some time window, that may be Poisson at a fixed time. But if I look at it over time and collect these events, this rate may be changing. You could also have a Cox process. So lambda t here is stochastic. And then you could also have, I mean, this rate could vary continuously or discretely. So this brings me to some prior studies on flare waiting times. There's been a lot of empirical work on this. And they've identified power law behavior of the flare waiting times rather than exponential, particularly in the tails of the distribution.
Excuse me, could I interrupt
Please, yeah.
the question? Earlier on, you made the statement that a lot of people assume solar flares follow a Poisson, or a Poisson process, and you nicely distinguished the constant rate Poisson process with a variable rate Poisson process.
Mm-hmm.
It's obviously the rate of flares changes over time in the solar cycle. So to be a little bit blunt about it, why would anybody think it's a constant rate Poisson process? It just, on the face of it, it can't be because of the if nothing else, the variable rate of flares in the solar cycle. So maybe I'm just probing at a semantic issue, but it's from the beginning, it couldn't be a constant rate Poisson process. Is that a fair thing to say?
I completely agree with you. I mean, all the analysis I've done, just like on my own, that is true. I mean, just the solar cycle itself, if you look over like a given solar cycle, we already know that the rate varies. So it's kind of immediately obvious, but people still make this assumption. That's the kind of the point I'm making. And Vinay, if you want
to. So there are two issues, right? So one is the variation over the solar cycle, which, as you point out, Jeff, is obviously is very obvious. It's there. And also what might happen over timescales of a month or so, over 1 or 2 solar rotations. I mean, is that really is the flare rate varying then? So I suppose we should be clearer about this, make the distinction that when we explore this this overdispersion, it is on small time scales, not on a scale where it's where the solar cycle has an effect.
Yes.
And also bullet point number 3, I think will expand on that.
Yeah, so I will actually dive deeply into that, but I think you make a good point that immediately obvious, if you're talking about the time scale of like the solar cycle, that's very clear it's non-stationary. So why make a stationary assumption? But part of my results are that even if you look at a smaller time scale, like Vinay mentioned, we do actually find evidence that we should be questioning this Poisson assumption. Regardless, I mean, studies, particularly at least some that I've seen with respect to stellar flares, still make the stationary Poisson assumption over some time window. So even if this is immediately obvious, this is still being done, which I hope to draw attention to that.
Sorry, this is, if I understand right, this is the whole point of this work and your talk is to deal with that variable rate Poisson process. But just to probe a little bit more, suppose the rate is never constant. Suppose it's continuously varying. Then you could argue there's no time scale on which you would want to look for Poisson distribution in the fixed rate context. And that's where what you're about to talk to, I get about Bayesian blocks to find, I think you call it in the paper, approximately constant or approximately stationary. But sorry to interrupt the flow of your talk. But this is really quite interesting, and it relates to something I've been struggling with for a long time with regard to AGN flaring activities. So anyways, sorry, go ahead.
Oh, no, thank you. Yeah.
But now I get a little bit confused. So I saw the key thing here is not about a constant versus variable rate, is whether it's Poisson or not. Because
True.
because even it's a variable rate, it's still not Poisson. It's, right? I thought that was the key distinction because the other one is well understood. Am I right? The work is not about constant rate. Nobody's arguing for that. Is saying you shouldn't make the assumption even the rate is variable, which you should do it in the first place.
Yes. So that is, as I take you through like kind of the results, that is the key takeaway, that even if it's variable rate, I do focus a little bit more on discrete time blocks, so like piecewise constant, but still varying. So at like the scales of months or several months, you still shouldn't make that. I don't go too much into continuously varying rates, but regardless, yeah, the key takeaway is any time scale, or whether it's piecewise constant or continuously varying, we should not be making the Poisson assumption, or at least you should be checking before you do.
Okay.
Yeah.
And maybe just to add more confusion on top or something like that, don't forget there are two processes, there are two random processes going on here. One is the variable flare rate process, and the Cox is sometimes called a doubly stochastic process. The other one is the observational error process.
Yeah.
And I think what's going on in a lot of data in astronomy is that the error process, you could legitimately say is Poisson, or in other words, uncorrelated errors, whereas the other half of the doubly stochastic process is variable rate Poisson, and very hard to pin down in terms of the terminology of a constant rate Poisson process. But anyway, so sorry, another possible tangent there.
No, that's important. Now you inspire me to say something more. Because there is a subtle point here. Let's say we know it's not a Poisson. Now we know if we use a constant, it's terrible. But if I'm using the variable rate, right, there is identifiability problems, like, because every time I only observe instantaneously, at least in theory. Can I have some variable in the rate itself to absorb the non-Poissonness in the measurement error? Because you have two processes. In the end, you only observe the marginal. So that itself is actually like for practical purpose. I'm not clear.
I think it is possible to mimic a non-Poisson process with a variable Poisson variable of
that's what I meant.
Poisson.
Yeah.
But I think okay, I mean, I don't want to scoop the talk again. I think you're going to talk about this later, right? It is even if you have a constant rate Poisson process, you end up not having a Poisson process, right? So I think at this point, all we're demonstrating is that you cannot get a pure Poisson process on this one.
The observed process,
Even if you have, anyway, I'll let you.
Vinay is alluding to what we're going to get into, but it's very complicated. There's a lot of levels to this, and I think up front, inherently, I mean, this is non-stationary in nature. But I'll take you to like looking at different time scales first, and these are great questions, and I think I'll address at least some of them as I'll continue, which kind of my next slide is related to this. So really quickly on the waiting times, I mean, what I find interesting is that we make this assumption related to the counts. There are a lot of studies that already say, well, there's a relation under the Poisson process. You'll have Poisson counts, and you'll have exponential waiting times. We have several studies looking at the waiting time distributions that say, well, it's the power law. You can explain this power law by discrete or continuously varying rates. So why are we still making these assumptions about the counts being Poisson distributed? And then also there arises the question, which you kind of asked, was, well, why do we have this non-stationary behavior? I think one, depending on the time scale, one reason is the solar cycle. Another, maybe we have synthetic flaring. So maybe these events are not independent, or what Vinay kind of alluded to, and what I'll get into later, is maybe we have some unresolved latent sub-processes. And then kind of the question I was asking already, which is what about the count distributions? There haven't been many studies looking exactly at the counts. It's kind of just easier to look at the waiting times, depending on what you're doing. But we still make this assumption. So should we still be making a Poisson distribution assumption for solar and stellar flares? Which I think we can say no. But I'll kind of give you the reasons.
Has that been a standard for when trying to project solar phenomena onto stellar objects, was to assume that the stellar processes were Poisson?
Yes.
Okay,
Yeah.
that's been a kind of long-standing assumption.
I mean, everything that works in the sun also works in the stars.
I hope so.
Oh.
Well,
But yes, I actually reference a paper that they derived some uncertainties, Proxima Centauri, I believe, and they looked at the energy distributions and they give some error bars, and they say explicitly in the paper these are from Poisson assumption with related to the counts. So this is common, and which yeah, so I'll get into that more later. But just really quickly, just with respect to the data we're using, I want to give you this background. So we're using the GOES flare database. We use the X-ray sensor, 1 minute average flux, and the 1 to 8 angstrom band. And then these in our data set, we're including flares from July 1996 to 2019. So solar cycles 23 and 24. And then our key properties that we're going to be needing for this analysis are the start, peak, and end times of the flares, the peak flux, and the total energies of the flares. And then what allows us to do some of the analysis is that for some, though not all, flares in the catalog, we do have the solar disk locations and the active region assignments, which allows us to do analysis on a per active region basis. So result one is that aggregated flare count distributions are overdispersed. So if you, before I jump into that, if you just look at the solar cycle, like and look at the counts, frequencies for different flare energies or classifications, it's immediately obvious you have some non-stationary process. But suppose that, like some studies have already done, you find these rate constant blocks using Bayesian blocking methods. And so essentially you use these methods, you find piecewise constant or stationary discrete blocks of time for which the rate is constant. Do we still have a Poisson distribution in those time windows? So we check this. So we identify in total 342 distinct rate constant time blocks using the Bayesian blocking methods. We fit a Poisson distribution to each of those blocks. So we look at the counts per time per time bin, and then we evaluate the goodness of fit and check for overdispersion. On the right side of this slide, you can see the probability plots relative to the Poisson distribution. I also give the rate for each. I believe these are the top 12 blocks. So they have the most flares. And I give the rate along with the variance or the square root of the variance. So you can do a quick visual check. How does this look? If you have to see large deviations away from that orange line, basically if they go outside of the gray region, that constitutes a poor fit to the Poisson distribution. Then you can just check what the variance, does the variance equal the mean here? If not, we have overdispersion. And for about 20% of these time blocks, we have that the Poisson distribution is an unreasonable fit. So even within rate stationary time blocks, where we would assume that it's a Poisson, so this smaller time scale, we still find that for 20% of these blocks, that they are non-Poisson. And of those that are not Poisson distributed, or Poisson is not a reasonable fit, we have that 87% are overdispersed. So of the cases for which we have an unreasonable fit, 87% of those blocks are overdispersed. So that's kind of the result one, which is, interesting to note. I think this is just a good exercise on why you should check these assumptions. It's not immediately obvious that these are Poisson distributed, but again, that's only 20% roughly of these blocks. It is not all of them. The next
Can I interrupt?
result.
Sorry. This is David Van Dyke. I'm just wondering, 20%, it's not zero, but it's not enormous. Do you have to worry about false positives? You must be doing some sort of statistical test.
Yes.
With your goodness of fit.
Yeah, I don't do anything like a Bonferroni correction or anything like that to control this.
Like, what is the level of the test, though?
This is I'm setting critical value to 0.05, so 5.
So maybe about a quarter of those could about a quarter of those could be just false positives as well.
Yes, that is a fair. Yes, that's true. Now of those, I think really I'm just drawing attention to, with the goodness of fit test, yes, we could have several false positives. I also include the probability plots, because I think you need to look really on an individual basis. What are the shapes? How do these fit with visual inspection? And then really just calling attention to, though, which is relevant, that of these blocks, which it's a unreasonable fit, and say, okay, a quarter of them we have false positives. Even still, almost 90% are overdispersed. In addition to that, I mean, you can look. We did Bayesian blocks.
I'm trying to interrupt again. So 90% of the 20%.
Of the 20%, which is, how many do I have? 30, let's say I have 30. So 20, 25, 26 of the, or like 24-ish of the 27 of these blocks are overdispersed.
I'd like to make a comment that is somewhat related to what David just raised. The Bayesian block analysis does not say that the rate is absolutely constant over the block. It says within statistics, it's constant over the block, and that may seem like a small point, but so it really depends on the context what the algorithm is telling you. For example, imagine a background light curve that has let's talk about a slow exponential decay, for example, with event data or something like that. If you fit Bayesian blocks to it, you get a nice piecewise constant step function representation of the decaying exponential, let's say. But the model is clearly wrong. Physically, you know that the signal is probably a continuous decay, but the best step function model of it is what the algorithm gives you. So that's kind of just a long-winded way of saying, suppose you take these blocks that are constant to within statistics and look at the block before it and the block after it to see what's going on. If that comparison indicates that there's a large change in the rate just before or just after these identified blocks, that would suggest that in reality, the rate is varying across that particular block. You just don't have enough statistics to show it. So I'm wondering if you could do an analysis and check these 12 cases or whatever you selected to see what's going on before and after, whether that makes any sense in sort of classifying these as really constant or just not even approximately constant. They're just I don't know quite how to put it other than just saying the model is forcing a piecewise constant structure on what you really think is probably a continuous variation. Does that make sense?
Yes, thanks, Jeff. That's an excellent point. It is true that yes, it's a good idea to check the before and after plots, just to make sure that there aren't, trends
Mhm.
that are visible. I should also point out that essentially this is like the what's the word, the worst case scenario or the best case scenario that we're checking. Like there is no ground truth, right? So, I mean, we don't know what the sun is doing at any given time.
Yep, yes,
So
exactly.
say if we look at what it might, stretch us where by any measure, any statistical measure, we cannot tell that there is variation. And Bayesian block seems like an optimal way of doing doing that check. And then checking to see what the whether we can tell what the variance of the flares inside are.
Mhm.
Well,
And
go ahead.
And I was just going to make the additional point that if you, it's difficult to see in these plots, but there are all these rates and the variance and the spirit of the variances listed on it. So you can see that even when the p-values are not very small, you still have that the variance is invariably larger than the mean. So the table that Josh has with the 30 or 20% is actually an underestimate, I would say.
But it seems to me you really want to do a test that you are accounting for the fact that you're doing Bayesian blocks first.
Mm.
I mean, the variances are always bigger, but that's the kind of way, that's how you deviate from a Poisson distribution. If there's any variability in intensity, it's going to make the variance bigger than the mean. So the fact that the variance is bigger than the mean most of the time by itself isn't, I don't think, that compelling.
Correct.
And 20%, I mean, like the very simplest thing, I'm a little confused. You said that there's no evidence in this data that that you could tell any variance in rate, but then you fit Bayesian blocks and you get a whole bunch of, it looks like, was it 342 distinct blocks?
Correct.
So there must be some evidence of varying rate.
Well, okay.
Now, if I could jump in, David,
Yeah.
I think the difference is what they're saying is there's no evidence for the rate varying across a given block, and in particular these blocks. They're not saying there's no evidence for a variable
Overall.
rate. Overall, yes.
But I mean, if you have, no one believes it's a step function. I mean, it's not
right, exactly.
It's a fine model.
That's what I'm trying to. This is essentially me reiterating the fact that this is like we do a formal analysis on this. Like, okay, let's say in the case that we want to assume that these blocks are we have rate constant blocks. Well, is that even true? I'm basically iterating. We still shouldn't make this assumption. That's what this is. I'm not trying to claim that really within these blocks, like definitively that we have a Poisson distribution of these are rate constant. I'm just giving a precursor to the rest of the analysis, which is, well, let's assume best case that we don't have model misspecification, that within these blocks, like there's not time varying or continuously varying rate. Let's say that it is a step function, right? What do we get? So this is kind of the assumption, at least from the literature I've read and in the way I've understood it, that this is how they try to fit and explain the time varying rate is through a step function through these discrete blocks.
Right.
And then I'm going through the process of saying, I'm doing that. Now, is this even a reasonable fit within those blocks with respect to the count distributions?
Right. I mean, I'd like to put it this way. You here identify the best candidates for there being a constant rate temporarily or, locally.
Right.
But I don't want to spend too much time on this point, which I think we've kind of reached a conclusion, but don't forget there's a variant of Bayesian blocks that it's almost never used, but you can plug in a different model and cost function and instead of piecewise constant, you can get piecewise linear or piecewise exponential blocks. And if you did that, I'm sure you would get different results for this because you would become much closer to to treating the underlying process as a continuous variation rather than a step function variation, which, as I think we all agree, nobody believes it's really a step function. But anyway, this has been a really interesting discussion from my point of view. I hope it hasn't been too much of a tangent for you, but thanks.
No.
But I guess this discussion reminds me, because to prove the point that we want to prove in the paper, this might be the wrong order to present. Even this is a kind of a natural way progressed, right? We look at it empirically to see, but to convince people without all the distractions. I mean, from my perspective, is because we have the theoretical without to show it's impossible to be Poisson. That's just let's see, right? And then you go with that, then you show that because every these empirical ones, there's always additional interpretations of you could have observed such things, right? So what do you think about how to?
This is a good test then.
There's
Seeing
good
how
test,
to
yeah.
react,
No,
maybe we should.
good question.
Yeah,
That's
these
a
are.
question. Empirically, there's all other reasons, especially everybody believes it, right? So that's
So these are great questions, and I'm going to move on because I think we're kind of reiterating the same thing that we don't buy this, right? There we go. So this brings me to result 2. Well, okay, what we were doing is we were looking in the aggregate, right? So we're finding these so-called discrete blocks, and this step function, right? Where supposedly we have constant rates. We're finding that's not really a reasonable assumption to make. Well, what if we actually look at individual active regions? So we're no longer looking at the whole disk. We're not taking all flares from different active regions, but now we'll look at these different groups. Maybe within the active regions themselves, they follow a Poisson process. Maybe it's stationary, maybe it's non-stationary. Let's do that. From the literature I've read, there has not been much work looking at doing this sort of analysis on a biactive region basis. The result, you kind of already have it here. They depart from the exponential distribution with respect to the waiting time distribution. They're non-exponential, and yet again, they're overdispersed. So this is to reiterate, the Poisson distribution is not reasonable to assume for the counts or Poisson process, so with respect to the waiting times. So just to give an overview of the approach, here, instead of the blocks, now we say, well, let's take each active region in our data set, construct the waiting time distribution for these flares, fit an exponential distribution to those waiting times, evaluate the goodness of fit, and see if there's overdispersion. So we do this with visual inspection. We also have goodness of fit tests. And then we're also calculating the overdispersion, or whether there's overdispersion. And for all of our active regions, so we were concerned about the sample size, so we wanted to make sure our goodness of fit test had sufficient power. We did a power analysis. You need roughly 50, a sample size of 50 for these goodness of fit tests. So we filter out active regions in our set such that we at least have 50 flares. I also include the results with at least 30 that we don't have as much power there. And so when we filter for at least 50 flares, we get 52 active regions. Of those, 52% have the exponential distributions not a reasonable fit. And if you do the same for a minimum of 30 flares, you get roughly the same percentage. You get about 50% of those not being a reasonable fit. So it's kind of mixed results. Half the time, exponential is a reasonable fit. Half the time, it's unreasonable. And looking at those individually, I should have included the numbers, I'm sorry, but a significant number of those are overdispersed. But now overdispersed not with respect to the count distributions, overdispersed with respect to the exponential distribution.
So my apologies, I'm going to inject some disgusting physics into your beautiful statistical analysis here.
Please.
So 50 flares coming from a single active region, that's a lot to ask for an active region.
Yes.
So why did you select that number in particular? And was it, at what point do you feel like you have enough statistical significance there to actually infer whether something's overdispersed like this or not?
Yeah.
Is a statistics question.
Yes. It is. It is.
Follow me and fit if I fit.
So there is a very good reason. So we use the Anderson-Darling test statistic, but I call it the corrected Anderson-Darling test statistic because we're actually estimating, so we're testing whether or not the given data is a good fit to the exponential distribution, but that test is determined by the parameter lambda, so the rate, but that test, so like our null hypothesis is determined by the fitted parameter itself. And so the distribution of the test statistic changes because of that. So we don't base this off of like the theoretical expected distribution of that test statistic. We do like a simulation approach. So you think just bootstrapping. Anyways, we have this goodness of fit test. All that to say, we wanted sufficient power. So to reject, we want sufficient power to reject the null hypothesis that it's a reasonable fit and reject that it's not. We want sufficient power to be able to do that. I ran a power analysis, so with different true underlying distributions. So for example, I'll show this later, but I have some slides showing this. So where under the null, we assume that it's exponential distribution with this estimated parameter. And then we take a selection of actually true distributions for which the data was actually generated from at varying sample sizes and varying distributions with respect to how similar they are to the exponential distribution.
Okay.
Basically, 50 is about the sample size that you need in order to have sufficient power to reject, so to have sufficient power.
And you got about, looks like almost 200, a little under 200 activations that satisfied that?
52. So
52.
for so
okay.
if you can see my cursor,
Oh,
so minimum of 50 flares. There are 52 active regions that meet that criteria. Half of those are non-exponential, or it's not a reasonable fit. And then if we lower that number to 30, although we don't have as much power, we get about 144. The percentage is roughly the same. But that is a good point. That is a lot to ask of active regions. So we aren't necessarily including every active region in our analysis to draw these conclusions. We're only talking about active regions which generate, I guess, a large number of flares.
It's going to be active regions that, like, right on the eastern limb have just started emerging or actively emerging as they go onto the disk, and you're seeing it through the full rotation, full half rotation. So the issue, a couple of issues I have here. So what motivates the hypothesis, the original hypothesis, that this would be an exponential, that this would be exponentially distributed?
Good question.
Because the way I see it, like, because I'm thinking of this as a physicist, I'm like, this thing has energy, it's storing energy actively as it's emerging. So it's impulsively releasing that energy, and every time it's going into a more, assuming that emergence has stopped, it is going into a lower and lower and lower energy state.
Yes.
So is that where you're getting it, or?
No, I mean, just this last week, there have been 3x flares, right?
Yeah.
And the latest, and the third one was brighter than the first two.
Mhm.
So I don't think you can say that it goes.
No, I'm not saying that. I'm just saying that, bulk over time. Well, you're not really focusing on the energy, you're focusing on occurrence. So,
Occurrence.
okay, and waiting times. Okay, so my physics brain told me to look at energy. But,
No. Energy is the right thing to look at. Yeah.
So the second thing I'm worried about is kind of something closer to like a Malmquist bias, where as you get further into like solar maximum, the actual X-ray background is going to start creeping up into those upper B and even lower C levels.
Okay.
And when that happens, you're necessarily going to be unable to detect, at least with X-rays. It'll be, sometimes it'll be a lot easier, say in the far or the extreme ultraviolet, you're actually going to be Malmquist biased below a certain threshold of detection. So I fear you might be, not actually getting the most active regions by looking at this. So
I think that's an excellent question. I think the broad question, I do not understand physics, but I think that you're basically saying, is there a selection bias in the way we selected these data themselves? Actually, even the data is up, the whole thing up Poisson, the selection process itself can create something of these natures? I think that's an excellent question. We need to at least have some way to say, I'm sure every selection has some bias there
Mhm.
that is not enough to overwhelm the answer. Otherwise, people say, well, this is not really a reasonable proof for
Mhm.
anything we
Mhm.
were trying to prove. That's
Yeah.
good. That's excellent point.
Because what I'm seeing here is that you're just picking out the most psychotic active regions that ever existed. So, and I don't know if that's truly representative of what.
Yeah, that's a very good point.
I'm not sure that the, what's it called, the detectability criterion matters that much though, right?
In the X-ray, I feel like it would.
I mean,
Yeah.
no, true in the sense that, yes, we will not see any B flares or
Mhm.
maybe even C
It
ones.
depends on the ghost XRS, because like
Yeah.
before, right,
Yeah.
right, like it wasn't as calibrated. Maybe now it's a little bit better calibrated, but it still has some issues with thresholding.
Sure,
What B class flares or A class, like if
And-
you're solar,
and-
yeah, if you're like a solar maximum, you are gonna have like a normal B class.
sure.
Activity.
And also, the closer you get to more flares, they all start overlapping.
Yeah,
And how do you know what's one flare versus two flares
Exactly.
is overlapping?
Yeah.
Or a cascade of flares, right? I
Mhm.
mean, so there is that
That's true.
ambiguity too.
Mhm.
So when somebody says flare, well, in this case, when
yeah,
ghost
it's very
person,
subjective.
ghost person says flare, it is an event
Yeah,
which might last for some time, right?
yeah, it's very subjective, because you
Um,
can have like a depth, like.
Yeah,
like-
yeah.
I thought only statistician is subjective, but I'm glad to hear that. No.
But the point that I'm trying to make is that, I mean, regardless of that.
Hmm.
What we are saying here is simply that, even if you have all these flares. And you find that, so essentially M and X class flares
Mhm.
that you see in these psychotic active regions. They are not nicely, they're not, even within that active region. It's highly active region, highly active region
Mhm.
is not represented by a simple single constant flaring rate.
But do you expect that? I mean, I'm wondering whether
Now,
can we run a simulations where you know what the things are? We do this highly psychotic selections to see if we can produce results of this nature, or even with the regular Poisson.
Assuming we actually understand like what the magnetic field is doing in
Yes.
3 dimensions, that's always the biggest
Yeah.
limiting factor.
But the
So-
I'm sorry to interrupt, the statistical model, correct me if I'm wrong, Josh, but the statistical model here is quite simple. It's just a homogeneous Poisson process, and the only parameter is the rate.
Okay.
That's
So
correct.
a simulation of this,
Binaries,
what we're
a half
doing,
and
what's being used to compute these goodness of fit statistics and things would be incredibly simple.
Yeah.
But does that, I mean, this is not simulation results, right? This is
No,
real, this is selective results, right? Not
Yes.
simulation results.
Yes, yes.
So
No,
still the
but the all of the statistics, rejecting the null hypothesis, the power, the 52%, all of that are from a very simple model, right?
Yep, yep. So the model is quite simple. Just from what I'm hearing, I think we do have this selection bias problem, of, well, we're selecting active regions that produce a large number of flares, so highly active regions. I'm not gonna question the physics.
The mental state.
Yes, yes. But in addition to that, I mean, we have a sensitivity problem. So there's this thresholding issue, which I actually have some slides on. This is a problem we've worked on too, is we can't detect all the flares. One of the questions I kind of explored for a little bit, it's been a while, but I think if you do this set filtering, so we set this this filter on, okay, maybe we only observe C class flares or higher through statistical simulations, not some complex physics simulations. I think you still get an exponential distribution. The intuitive way I think of this, or just to think of it, suppose you have like a traffic light and you're looking at the number of cars that go through this traffic light per hour, or you look at the times between cars going through the intersection. if you just look at all the cars and you don't group them out, let's say that follows a Poisson process, you have exponential waiting times. Now, what if we only look at the red cars that go through the light?
Mhm.
If you do this kind of filtering, do you still get an exponential distribution? Maybe you just have longer waiting times. Or if you only look at the blue and red cars and ignore the green cars, right? So there's this, I would want to work this out before I make any claims, but I think if you do that kind of like consistent selection bias, in the sense if we assume that these flares, like A class flares, B class flares, C class flares, maybe they each occur at their own rate. But you filter them out consistently, so you
Yeah,
filter out all the A class flares, you still have a Poisson process.
Poisson rates add.
Yeah, it's just additive. Yeah.
Got it. Okay.
Also CHASC question, let me have another question. So for example, usually for a certain active regions, the magnetic field configuration is kind of the similar or same during this all this time period. So that means for an active region, all these samples are not independent.
Mhm.
So I don't know if that will also you should affect in this in your statistical results.
So what are
So for example, in this 52
Mhm.
oh sorry, for example, for certain active region, all these 15 flares, they have the similar magnetic configuration.
Okay.
So that means these samples for certain active regions, they are not independent.
You mean the power may be even
Yeah,
lower than you thought?
translation.
That's a good
Oh,
point.
yeah.
I see.
Yeah, no,
So-
absolutely, yes.
Yeah,
That's a
so
good point.
I think, yeah, you should fetch this.
So that means but did you, in your test, did you assume they're independent, right?
I am. This is the simplest we can get. We assume that they're
Okay, so that is the self, then you need the
So-
effective sample size.
I just want to make the point that we are not trying to model the run of the flares.
Yeah,
We're not trying to say, okay, this is the evolution of the field and how, this might set off the flares at certain times or any such thing. If we wanted to do that, then yes, then we have to consider all those things. At this point, all we're saying is that, okay, we have this run of flares
yeah.
above a certain threshold, with all the attendant problems of detectability and all those things. Does that look stationary?
Yeah, I understood that. But for example, we have 10 active regions. Then each active region we have 50 flares. So I just take a very extreme example. Like these 50 flares are same for a active region. Then basically we only have 10 flares. But now you actually take 500 flares into your samples. So that can have a
Result
problem.
3.
Hmm?
Oh.
I think that's the next slide.
Oh,
Yeah.
Okay.
So we have another result. I think this might address this question, so I'll move to it. Result 1 and result 2, all this to say, we're just really questioning. We're trying to model the flares as a Poisson process first at larger time scales over the whole disk, just in these blocks. We find, well, that's questionable. Now we're saying, what about within active regions? That's questionable. And so what we have next is we actually talk about the observed counting process, which you can think about as a mixture of temporally overlapping active regions, which Bernard, Shelley, Vinay, and we've worked on this quite a bit to kind of break down, well, at least with respect to what we're observing, what if we make some simplifying assumptions? Do we actually have overdispersion still, or do we observe a Poisson process? So I'm going to explain this. I think this will answer.
Before you go there, can I ask a statistical question, which I actually never asked this one before, and I don't know the answer. You have been talking about overdis on the Poisson, you talk about overdispersed on the exponential, right? These are two different overdispersed.
Yeah.
Is there a relationship between them?
This is what we've been talking about all morning. It is not a clear relationship. It is not.
No, it's not clear to me.
It is not.
Because it depends on how you deviate from Poisson leads to the other thing, right?
Yes,
But
exactly.
it'd be actually really interesting. This should be part of your PhD thesis. this will be really tricky problem to figure out when these two things, like if you see both happening,
Mhm.
maybe that points out to a particular kind of deviation from the
Mhm.
Poisson that might be useful. I mean, there gotta be some characteristic there, right?
Yeah, that is a great question. We've talked about this. I've been like racking my brain over this for the last bit. And I can tell you with the data, there's correlations between if one is overdispersed, the other is overdispersed, but there's not like a simple transformation you can do.
But at least you probably can come up with a 2x2 table, both over dispersed, one
Yeah.
intervals, like,
Yeah,
you know,
yeah.
having these examples,
Yeah.
so you at least convince yourself
Yeah.
it's not in some direction.
Yes.
That
yes.
probably shouldn't be too hard.
Yes, that would not be. But in terms of like,
The
can
general
I derive,
yeah,
like
okay.
if this is overdispersed, if counts are overdispersed, is the exponential overdispersed? Well, it depends on like, well, how is it overdispersed?
Yeah,
We have a lot of
that's
zero counts, we have a lot of larger counts.
Because you
with
could have like
exponential-
overdispersed by happening very fast.
Yes.
On the count, then the waiting time is bimodal, you know.
Yeah,
could be-
is it bimodal,
I
is it unimodal?
I can see that, I can see that.
It is not intuitive, I
Okay,
tried to figure
okay.
this out,
I see.
but that's a really good question.
Okay.
So
Got
maybe
it, got it.
I'll note that for the PhD.
We should have a contingency table in the paper.
That's actually, yeah, we'll do
Yeah,
that.
yeah, for that, okay.
So this brings to result 3, which is kind of result 1 and 2 are empirical, and to say that Poisson assumption is questionable. We don't really know that we should be doing that, but let's make some.
Oh, it's 3 o'clock, so can
Oh,
you
okay.
finish in 15 minutes?
Yeah, oh, absolutely, yeah. So we can let's make some simplifying assumptions. Let's build an observed counting process to explain let's explain the observed counting process we have on our hands. So as I mentioned before, we have this overdispersion. What contributes to it? Well, we have a non-stationary flare rate due to the solar cycle at smaller time scales. So even within active regions, maybe this rate is varying or there's non-independence of the flaring events. And then lastly, well, if we're looking at the whole disk, let's say we can't resolve the individual active regions, which is often the case for stellar flares. You're just looking at this point source. But we know if another star is anything like the sun, we probably have active regions, and those are probably generating flares, and they're probably generating flares with their own rates. So there are these unresolved latent sub-processes, sub-Poisson processes from active regions that are overlapping in time, possibly space. So in the plot on the right, this is just empirical data. So the data I have, if we look at each of the active regions in our data, calculate the flaring rate, and then plot that over time, we can see the step function. Now, this is the flare rate with respect to only flares which are assigned to active regions. So we're only looking at the individual active regions. So if an active region comes and goes, there's a rate, and then it drops to 0. And so you can see that there is this step function with respect to the active regions, and you can see this is highly correlated with the number of active regions which are overlapping. And by overlap, I mean there are 1 or 2 or more active regions occurring at the same time, each producing flares. So if we're looking at a star or the sun, and let's say we don't see the active regions, we know each are producing their own flares and at their own rates. And so even if within an active region, that rate is constant, which is questionable, let's assume that it is. If we have multiple active regions coming and going and overlapping, the rate is then going to be non-stationary. And that's what we'll observe. That'll be the observed process. And we might not actually be able to resolve those latent sub-processes. So the Poisson processes from each of those individual active regions. And so we had developed this overlapping active regions model, which I'll kind of describe here. So we have, we're going to model the observed event count process, so N of T, the number of flares, as the sum of K Poisson sub-processes. So think of this as your K active regions, each active only on some interval, tau sub K to tau K plus V sub K. And for each of these K sub-processes, we'll have an onset time, so the time that active region comes and starts, a duration, so how long it lasts, and then we're going to assume for the sake of simplicity, that within a particular sub-process or active region, that the rate is indeed constant. And for each of these sub-processes, we'll assume that the counts, while it's active, are Poisson distributed. And so
Sorry,
I have my-
sorry, I'm a little confused at this point, and that's a crucial point. You say that within each subregion, the model is that the Poisson rate is constant, that it's a homogeneous Poisson process, but your formula has a time dependence in it. So I'm confused. Is the rate in each sub-process rigidly constant?
The count is with respect to the observing time. So if I say start at time 0, we'll have 0 counts. If I go from t equals 0 to t equals 1, we'll have we expect lambda times t. So whatever t is, if that's like your units of time, say 1 hour or hours. So if we look from 0 to t, say t equals 1, we'll have a rate, or we'll have a Poisson distribution with a rate of lambda times t, so 1. But if we look over a longer observational period, so t equals 20, it'll be whatever the rate is times 20 is your expected value. So it's constant in the sense that the rate is not varying over time, but as you have a longer observation period, you're going to necessarily accumulate more and more events. Does that answer your question?
Oh, well, I have to think about it. I guess it does. What bothers me is the well-known thing that if you add together several homogeneous Poisson processes, you get a homogeneous Poisson process with the sum of the rates. So
No, you
that's
don't.
not
don't.
what you're
Yeah.
doing here. You're doing something
You-
different than that.
Yeah.
and I
Yes,
don't
you do.
If
You're
it's not-
right. If the support with respect to the time of the
same.
process start and end at the exact same time. But if they don't,
Yeah, okay.
that is exactly what we're going to get into.
So that's what your model does, is to take account variable support, not variable
Yes.
rate. Okay. got it.
Yeah, exactly.
Yeah.
Exactly.
Yeah. I mean, we're just doing this is like the simplest one to say, even just deviates from you starting different time, it's already get you non-Poisson theoretically.
Mhm.
So basically saying how other things could be so non-Poisson, right? The whole point is we try to come up with the simplest one and it's just deviate on one thing, like the starting different time.
Yeah.
There's everything part, but that's already enough to kill the Poissonness.
Yeah.
Yeah.
Yeah. So this is the model, right? So we'll have these k active regions. Within the active regions, we are making the assumption, which you can question, but to simplify, that the rate's the same. And then the only really what's changing here is that the times at which these sub-processes are active, they're coming and going, just like active regions actually do. And just to reiterate, you are right. If you were to take these two homogeneous Poisson processes, if they had the same support with respect to time, then you would just add the rates and you get a homogeneous Poisson process. But here, they're coming and going, right? So they're, like I showed you in that step function, we'll have an active region or sub-process start, and then it'll go away. So the rate is going to be non-stationary. And this, besides the fact that the rate within an individual active region, we're assuming it's constant, this represents roughly what kind of our observation process is that these active regions are coming and going and they're producing flares and they're going away, and sometimes they overlap. So we're asking the question, do we expect to have overdispersion here, or is this still a Poisson process, even with these simplifying assumptions? And so you can describe this observable process by the counting function here, which is n of t. This indicator function, all it's doing is just ensuring the sub-processes contributes only while they're active, and then it's fixed after that. And then these latent parameters and the number of sub-processes, so k, and then tau v and lambda, so that's your flare rate, the end and the start time. You can set a prior on this, or you can fix them. And so to the point, to reiterate for a third time, but specifically with this model, if we fixed k to whatever number, and we fixed lambda to be the same for all k, and then we had disjoint support. So one active region is active from time 0 to time 10, for example, and then the next is from time 10 to 20 and 20 to 30. You'll get a homogeneous or stationary Poisson process with the rate lambda, or you could do this kind of stacking where they're active for the same period. and then you would add the rates. So I'll kind of skim over this because we're short on time, but we can use the characteristic function to get the moments, and then we can kind of get the properties of this process. If you aren't familiar with the characteristic function, think of it as the moment generating function, that you have I and the exponent. It's every, we have a characteristic function for every random variable. It's easier to work with in some ways. So let's put this into the simplest possible situation. So we're going to say that we only have two active regions, or two Poisson subprocesses, each with some rate greater than 0. And then we're going to fix the start time so they both start at the same time. And then the only thing here that's going to be random, besides the generation process of the events, is going to be their lifetimes, which will be distributed as exponential A. So 1 over A will be the mean duration. So we get the mean duration of the active regions to be 1 over A. And we can derive the first moment. So that will give you the expected number of flares. And then you can get the second moment and use that to get the variance. And so in simplifying this, we have this first term here, the expected value. That's our mean. If you take the limit, I believe as A goes to infinity, there's a T, as T goes to infinity, you should just get, as T goes to infinity, you should get 2 lambda over A. And then your variance is the expected value times an overdispersion factor, which will always be greater than 1. So even in the simplest case, we're saying we have 2 active regions, they start at the same time, and then they could end either at the same time or one before the other or one after the other. They each generate flares at some constant rate. But if we look at the expected value and variance of this observed process, just with 2 active regions, we're going to observe overdispersion.
But when the factor is equal to 1, because the special case is if you have a fixed, you're generating the starting point as the exponential itself. The 2 processes you say they start at the same time, but they could end at different times. Okay, but the ending different time is controlled by which variable?
A.
By A. So when if A set equal to 0, no, A set equal to infinity, then which way? That because what would be the process? How do you set A that they were ending at the same time?
Oh, then we're assuming that the lifetimes are exponentially distributed. So you just have to set that to a constant. So you'd set A here is the exponential parameter.
Okay, this way of setting the fixed domain is not a special case.
So if they last forever, I think that's the limit of A going to 0.
No.
Mean duration 1 over
1
A,
over 0.
yes.
Yeah.
So if A goes to 0, then they last forever. So it's like a theoretical Poisson with.
Oh, so that has a rate, and in that case, all I'm saying, in that case, that exponent that factor should be equal to 1.
Yeah.
Is that right? If you look at the next slide.
Oh, okay.
If A goes to 0, that whole thing should go to 1.
This?
Yeah.
I believe so.
Because that's the case, then you have to recover that.
Yeah.
Right. But it's not obvious yet. Actually, the way you wrote it, I think you need to rewrite it. It has a limit. It has to be. The first one doesn't have a limit.
Yeah.
So it must be something. Okay, I see how this thing, it's all blow up. I see you need to rearrange it. To rearrange in a way that's obvious that it's A go to infinity, it's 1.
Yes. And then
A goes to 0.
A go to 0, sorry. A go to 0.
And as T goes to infinity, this here will
go to 1. Yeah, that's fine.
Yeah. So the result here is that in the simplest case, we have this counting process that we observe where we can't really, here in the model, we're differentiating them, but the actual process that we observe would be the accumulation of flares from these many active regions. And in the simple case, which is 2 active regions with constant rates, we still have overdispersion, and this is the overdispersion factor. It's not really too pretty, but so
there's a quick thing which, sorry, that, I mean, we can do better than this, but even this will suggest that if you have an estimator of the overdispersion, you can estimate what the A is. Because the factor allows you to estimate what the A is, right?
Okay, and thought of that, yeah.
Right, because otherwise we could, although you probably can do better than do other fancy instant moment estimator.
Yeah.
Giovanni has a question.
Yeah, please.
Hey, Josh, great talk. I have a question about the way you're modeling the non-stationarity. So have you considered, say an approach where, so the parameter lambda is a smooth function of time, instead of looking at these, say, blocks? And my other question related to that is how you choose the VKs.
With respect to the non-stationary where lambda is varying with time, have not looked at it. Specifically with respect to this model, no. There is some literature not explaining this counting process, but they do treat this as a continuously varying rate parameter, but we haven't looked at it in this context. And what was the second question?
Well, I was thanks for your answer. I was explicitly referring to the class of locally stationary Poisson processes, where the lambda is smoothly varying over time, and there are some nicely established properties. My second question was, so you sum up the indicator variables, say t from say tau k plus 1, and this is clear. It's very clear what you're doing. My question here is how you choose the VKs or the new case. I don't know, this is V or new.
Yes, the way we choose that, the durations are from, where do we go? So the lifetimes, those are given by an exponential distribution. So those are just randomly drawn. And then, well, if you were to simulate, but so those are drawn from an exponential distribution. So those are exponentially distributed.
Well, I'm asking this question because I'm familiar with this averaging, and so using say a parameter that varies over time it's actually you impose very few conditions and it's computationally faster to smooth.
Oh,
yeah, way faster. You don't need to go through the random sampling. But anyway, so this is great stuff. Thanks for your answers.
Thank you. Okay. That's good to know. We'll have to look into that.
Giovanni, I'll expect an email from me.
Say it again?
Expect an email from me asking for more details.
Sure.
And sorry, I have a comment that's related to the first question. I can't see who asked it, but the first question that was just asked. So the basic, if I understand the basic thing you're trying to do here is that physically there's a continuous process, that sort of propensity for flares to occur, which you don't know, but what you observe are events spawned by that continuous process in some sense. So you're trying to test, not that that's a variable process, because it's obvious that it varies. You're trying to test, does it vary in some sort of Poisson-like way? And the way to test that is to look in bins and see if it follows the Poisson distribution. I mean, in a crude way, you're looking at other things like interval distributions and so on, but suppose you were testing based on whether the bin counts of events satisfy the Poisson distribution. So you pick a bin size, and I would argue that with that bin size, there was evidence for overdispersion. You could argue, well, you just made the bins too big. And if you made the bins smaller and looked at smaller intervals, you could find an interval small enough so that you could find a Poisson rate that would give you exactly the Poisson distribution or within the statistics. On the other side, if with a bin size you chose, it looked like it was a good honest constant Poisson homogeneous process, you could say, well, those bins are too small. If I make them bigger, you would capture the variability and find
Yeah.
overdispersion. So
Yeah.
that argument is that with any process, the conjecture is any process can be modeled either as a Poisson process or a non-Poisson process. And what you really need to do, I mean, this is a humble suggestion for what you should do, study this whole business as a function of bin size. And if there's some sweet spot in bin size where over a long range of choices, you get a good fit with a homogeneous Poisson process, then that's one thing. But if there is no sweet spot and you sort of continuously go from over dispersion to under dispersion, that says another thing. Does that make sense?
I think so. My question is, I think I see what you're getting at. Are we saying bin sizes with respect to, say, like an energy bin, and then you're looking at the counts for that particular energy bin?
No,
or
in
are you
time,
saying
in
bins
time,
with
just-
time bins, like
Yeah,
time
bins.
yeah.
And I'm thinking
Okay.
evenly spaced bins, or maybe you could
Yeah.
play with adaptive binning like Bayesian blocks. But let's stick to
Mhm.
constant bin size. Pick a bin size. I mean, it's analogous to stationarity. Stationarity can't be tested in general. You have to look at it as a time scale issue. Pick a time scale and find whether a process is stationary on that time scale. I think you have to pick a bin scale before you can answer the question. Well, like I say, as a function of bin size, I think is the key to this. But hey, that's just a
I
conjecture.
am not sure that such a thing exists on the sun. Is there, would you say that there is a common time scale that you can look at?
For what?
Evolution of
Right.
player.
What do you mean, Vinny? I'm just postulating pick a time bin arbitrarily, anything.
Yeah.
Seconds,
Yeah.
minutes, hours, years, whatever it is. Study the counting process as a function of, look at just the Poisson distribution itself, and do a test for how well the counts in that bin size fit the Poisson distribution. You generate some statistic for that and study that statistic as a function of the bin size.
And try to optimize it to make it look as much as Poisson as you can within
Right.
each bin.
It's,
Okay,
Yeah.
so
the sensitivity to the
right,
bin.
so
Yeah.
we have looked at, Josh has looked at timescales going from 10 days to 1 year. And does
For just across the entire disk of the sun, or?
across that data
Okay.
set, yeah.
Right, so,
I-
but you, so I mean, can you not look at one active region at a time? Because the point here is that the active regions come and go at different times, it
Yes,
seems to me. But so
They don't
if you,
usually-
but
Go
if
ahead.
you can look at them separately, that's not really relevant, but are there overlapping, you can't distinguish between them?
If they're overlapping, well,
My question is, are they overlapping and can you distinguish between them?
it depends. So overlapping temporally, yes, that happens. So they're occurring at the
Sure,
same time.
but can you
Physically, like,
distinguish from between them because
spatially,
if they're different
yeah.
places?
Yeah, spatially, I would like you can tell.
Yeah.
And several times you can probably.
not from the
but-
data set that we are using, but there are other data sets which let us
So, so why would you
Yeah.
mix them together then?
because
So that's the observed process. Like if you look at another star, you can't resolve active
Okay,
regions.
so if you're gonna do a different star, that's a different data set, that's a different problem that will have a different model. But
Yeah.
with the
But even in
sun,
the current data set, the ghost player data set does not tell you where the active regions are.
so but you just a moment ago said there was other data that you could use to distinguish them.
Sure.
Yes.
Yeah, yes.
So why don't
So-
you want to use that data? I don't understand.
We do. So that is, I have my future work, which is that ideally we get every flare. So we have this, and these are the limitations that people brought up, and these are really valid points, and we've thought about it a lot, is that one, we can't observe every flare for a number of reasons. both due to equipment sensitivity limitations, but also there's a detection algorithm which GOES uses, and it's not overly sensitive, so it won't pick up all of the flares that we think are actually happening. There's another issue of kind of, to answer your question, is that we can't always temporally or spatially resolve these flares. So like in this figure, we have 3 active regions in these boxes. And if you were to just look at the integrated flux over the whole disk, this is what the light curve would look like. And there may be, in these 3 different active regions, you may have flares going off, but if they're too small, they won't surpass the background flux, especially if there's another flare going off. So there's data we have. I think this is it so? Oh.
No, this is.
What is it?
AIA.
This
Oh,
AA 335.
This AI, okay. We do have access to image data. So, I mean, this is a long-term project, but I would love to be able, and I know there's some work that's been done with this, but I think with magnetograms maybe, but to identify the active regions, place some bounding box around it, track them over time, get the integrated flux, and then for each of those active regions, construct these light curves, detect the flares from those active regions, and then construct these distributions. I think that's what you have to do it right.
So the way it works is we do have the specificity to say the flare happened in a very particular location. So so it's true that GOES, at least the X-ray measurement system, yes, it's going to show you integrated over the disk of the sun, the X-ray flux, but it's very easy to see when there's a very localized emission of X-rays, because that's how we get our very definition of how we detect flare. So, but the thing is that we have so many things staring at the sun. They're staring at it in the extreme and the far ultraviolet, that can have far more that actually have the spatial resolution to observe that. Like the Space Weather Prediction Center does this all the time, where they actually just take the GOES flux map. They say, here's an X-ray anomaly. And then they can actually just go back, look at, SDO. They can go through every different temperature layer that they can to just see kind of where is this actual anomaly, so where is it associated with the temperatures we know we're observing in the far ultraviolet. And you can actually just pinpoint, at this time, it's definitely cross-correlated with that. So we definitely can pick out, locations quite precisely. I mean, if you're looking, say at SDO, you're only limited to about, 0.6 of an arc second, which is, which is pretty, you're going to definitely well resolve the structure of whatever happens there. I mean, the big issue now is that, say if you have 2 things that are very close together, these are not point sources, they're extended features. So who's to say that if you have a particularly aggressive magnetic field, and let's say you get reconnection at 2 different points, which sounds ludicrous, but I'm sure it can happen. So, and you actually get 2 different ribbons that are in the same area. So I guess maybe there could be an issue with those 2 overlapping, but that seems like, from a physics point of view, something very difficult to do. So I would push back on the idea that we don't have the ability to really pinpoint these spatially. So I think we do, because we can readily correlate, at least Space Weather Prediction Center can readily correlate these to figure out what active region they're coming from. So
No, I agree with that completely. It is just that so first of all, you can't extrapolate it to stars.
Yeah, that's the thing. Because
But stars are going to have a lot of differences, I think, Vinay. You're going to be looking way in the tail of this distribution. I'm not sure you just want to pick up your model from the sun and put it on a star.
Not necessarily.
No,
Not necessarily.
No.
Not necessarily. You can see as many. You can see as deep into the flare distribution on the stars. You can see on the sun.
No, definitely not. So you're going to be limited by the fact that you're.
You are looking at the tail.
Yeah, you're going to be limited by 1 over r squared, of course, but But the thing is that the excursions that we see, especially from like say MX flares, are so extreme above the background that even from, reasonably, I'm gonna say this, like within a kind of local group of of stars, it will be readily observable. Like we've observed flares on usually particularly lower mass stars that are kind of within our neighborhood pretty easily. So in fact, we can pretty well say that.
Earlier, we were worried about selection effects by looking at only the brightest ones.
Yeah, so I mean that's gonna apply no matter what. So
But stars are
Sorry.
different than the sun in that you
we
will
got a
be
physicist arguing with a
necessarily in
statistician
the
here. So what was your question again?
You're in the tail. To say that there's selection effects in the sun, but if you're looking at the tail of that distribution with a star that happens to have
Yeah,
all its
gonna be the
properties,
same.
just like our sun, Mike
Yeah, you're gonna get
I think it's
Malmquist bias regardless.
uncontroversial that you'd want to be careful about using a model from the sun on any old star.
I
okay.
agree. Other stars are not as bright in the sky as the sun.
No, David.
And that
no,
has
there is-
implications for how you model their data.
No, so we assume that the physics that operates on the sun is also the same physics that operates on stars.
So the
And,
selection effects is not something we worry about with the sun. By looking, we were talking about this earlier, right? By looking at the brightest, most persistent flares, that there might be an effect of that on the analysis. That's not, but now you're saying that if you do
brightest
that
and
for a
most persistent
star,
active regions.
What's that?
Brightest and most persistent active regions, not
Yeah.
flares. But
yeah, that's what I mean. Yeah,
yeah.
I see. So it's the active regions, not the flares, that were where you were worried about Malmquist bias. But by
Yes,
screening out the flares way in the tail, that's not a problem.
Okay, so we can see that the flare energy distribution is a power law over several orders of magnitude. And this seems to hold true even on stars. Yeah, even
But
though
that's about the brightness, right? But I mean, this is
well,
not a
in top
model for
energy.
that. This is a model for waiting times and Poisson in
no.
the event times.
No, that is the distribution of the energies. But
Yeah.
the idea being that if when you're looking at the tail of this distribution, you're looking at flares that are of a similar ilk.
So if you can look at say a G 2-5 star like the sun. We have done like sun as a star stuff where you just kind of you integrate over the entire disk and see how that compares to similar stars that you see out in the sky. We have noticed that we do understand that some stars, depending on their mass, will have very different interior structures and very different magnetic fields or magnetic field strengths than the sun would. So from a physics point of view, yes, it's true, physics is going to operate the same everywhere, but you can't guarantee that the star itself is structured like the sun. So we do notice that the smaller the star is, so if you're getting down to like M dwarfs, things like that, when they're very compact, they tend to have very strong fields and they tend to be way more active than the sun does. So there's a general trend that the more mass that you have along what we call the main sequence, so those are stars that are actively burning hydrogen, they are alive, is what we would consider them. So the higher you go up in mass, one, the interior structure of the sun changes, and two, the magnetic fields get far weaker. So we don't necessarily, I would push back on the idea that this is something that's scalable onto other stars. So from a physics point of view, I'm trying to think of this like an astronomer. So is that I've got my HR diagram. I know where all the stars are going to fit. I know what is burning hydrogen, what is not, what the interior is going to look like for some stars, what don't. So, and what I do know is that activity does not behave the same on some stars versus others. And I don't know how well that scales from the sun though.
We know that so for example, if we're going off on a tangent.
Yeah, sorry.
So if you look at the flare energy distribution on the sun, it is 1.8.
Yeah.
And it is close to what you would get from cellular automata or SOC type processes.
Mhm.
You go to stars, active stars, it's greater than 2.
Okay.
And that is already difficult to model as a similar process in the sun. So I agree with you that there is something else going on these stars that is making these slopes much steeper.
Mhm.
I guess what I'm trying to say though is that it is still, I mean, there's still flares that are still being produced
Yeah.
through reconnection processes. And there's still no scale
Okay.
that can be recognized as something that makes it Gaussian and not a Poisson.
So you're saying that we still are struggling to say that there's some distribution that we can scale from the sun onto other stars.
I mean, it is
Okay.
not directly scalable, but I would say that similar processes are happening. We just need to recognize what those processes.
But what if we observed every nearby G25 star and that was, just like the sun, very similar age,
Funny you
everything.
should ask, because there's a paper recently looking at test data where the Palermo people actually looked at G-type stars and found that most of them have similar slopes as the sun.
Okay.
Close to 1.8.
So there's scalability there, and
Maybe
you're assuming that they're not all at the same age, so there's different spin down effects.
there are spin down effects.
Okay.
And they also, well, that paper also pointed out that there might be a break in the formula, which means we can get a handle on some scale somewhere in the system, which would lead to a little slightly different physics.
Yes.
But all that is, I'm not sure why we're talking about it.
I don't know. I kind of got off on the tangent and I felt like yelling about it. So.
I think.
Well, because the model makes an assumption, or is working under the assumption that you can't distinguish the flares, which is clearly an issue on stars, but not clearly an issue on the sun.
So why you're asking how is it that whatever we are doing on the sun, how does it translate to stars?
Yes.
Okay.
So that's where I got into my crazy tangent.
Well, I think people still make the Poisson assumption on other stars, though.
People do
relevant.
make the Poisson
Yeah.
assumption on stars.
And I think we're just trying to demonstrate that assumption is quite questionable. And you will quite literally, you'll underestimate your uncertainties. There will be more variability. And won't get into the physics, but can we scale this to other stars? Maybe or maybe not. But in the limited studies I've looked at, they're still making a Poisson assumption, which in essence.
Let me put it this way, David. I mean, you remember our EVLAC paper where we quoted a flare rate.
Then it crazy flares. There's nothing like the sun. That's why I'm worried about.
No, but the thing is that we said that the flare rate was whatever, it was 2 per day or 2 per something, 2 per hour, 0.2 per hour plus minus something, and we based that plus minus something on a Poisson assumption. So it's clearly, even we have been making this assumption.
And
because my brain's constantly thinking, what does this mean physically? So, and what I'm trying to seeing here is that you're trying to say we're treating the sun, say, as a star. Sometimes we're not, because we're, breaking it down by active region. And we're saying, what can we do to, statistically infer what's happening on the other stars? You're not necessarily making a physical assumption about why the distributions are this way.
Yes.
That's what I want to know.
Right. No. So yes, that last part that Josh was talking about with the overlapping active regions.
Yeah.
That we are not saying that is the driving phenomenon that says that leads to the overdispersion. All we are saying is that is sufficient to break the Poisson nest.
We're looking for very simple example. Just very simple example. Just the one random star and finishing is enough cause the problem.
Sounds like he has a question online.
I'm sorry. Yeah, I keep trying not to interrupt, but it's hard for me not to. I wondered that with that result, can't you show that any non-homogeneous Poisson process is overdispersed? I mean, you're showing it when you have just a step function, essentially, when it goes from one rate to another. And it seems to me that you can generalize that, and it's just my intuition. Absolutely. That's why I said early on that the fact that the variances are too big is not surprising, because it's my intuition absolutely that if the intensity is changing at all, that you'll get overdispersion. I mean, it's just another source of variance, right?
I think that's right. I totally agree with that.
That is.
I think that the way we set up the model could be, we use the characteristic function, right? The compound of this kind of this overlap Poisson. I think that there's a general results, which we haven't done yet, which is just, you did the simple ones doing the mean and variance, and I think there's inequality. Because all we need to show is the variance is larger than mean.
It's bigger than mean, yeah.
At least you settle that's overdispersed, not Poisson.
Yeah.
And that we can settle it two ways. Either the results always holds, or you can characterize for which function, because we have the distribution of the starting point that does not holds. But it's almost, I mean, the other thing we could probably do is to show the only time they're equal is with the fixed.
It's flat.
That one I'm not entirely sure. You could have something very funny going on, like two arrows canceled with each other. Or, well, for the simple question, whether mean equal to variance, but that does not even say much about distribution. It could be still mean equal to variance that thing is not the distribution, right? And I think, I
was just going to say, have you done a careful literature review? It just strikes me that the homogeneous Poisson process is so well studied that I'm surprised no one's looked at that before.
Oh, I'm sure that someone look at that. We just don't know who they are. I'm sure everything's done. But I think to take David's point, actually, we don't even go that route, because we know that if it's a Poisson, what a characteristic function looks like. We just need to show that thing can never be equal to that unless this thing specified.
Jeff has.
Sorry, I have to leave, and I'd like to sign off with two suggestions. Well, I mean, the first one is, for what it's worth, ChatGPT is pretty good at about digging up references to what people have done. So I hesitate to even mention that. But don't forget, there's two handles to Poissonicity. The definition, really, in my opinion, should be independence. The crucial physical nature is, are the events independent? So the fact that when you look in bins and they satisfy some quasi distribution, the Poisson distribution, that's sort of a subsidiary thing. And you run into all kinds of difficulties with intervals and bins and so on because of that. But more fundamental is to look at the independence. So a conjecture is that the best way to look at this problem is to look at it from the point of view of independence tests, not distributional tests. But that's anyway. Sorry, I've got to sign off.
Thanks, Jeff.
Yeah, well,
very useful.
Independence in.
So
you're throwing darts at an interval. It's really what a Poisson process is, and the darts don't affect each other.
Okay, got it. Okay.
now you got flares occurring in an active region. We assume that every flare happens on its own, but what if one flare causes a higher propensity for another flare to happen?
Right. Yeah, that's the physical.
Sympathetic flare.
The sympathetic flare, even a flare within an active region, because you fundamentally change the energy distribution within that region. So
you set off one flare, there is more likely to be another flare.
Interesting. Okay.
Yeah.
I mean, that's
Especially if you brought in the energy, you could imagine, I don't know, it's physics, right? But the way to think about it is that the waiting times are independent. And if you have a very strong flare, does that make it more or less likely that there's going to be another flare? I don't know.
Because in general, it takes a lot of time to build up energy in a magnetic field. Takes far less time to dissipate that energy. And that's the fundamental issue we're looking at here, is how much time do you need to actually piss off the magnetic field to where it wants to get back into a lower energy state. And whether or not, when you actually go into lower energy states, there's still residual energy left over you could use.
There usually is.
So, yeah, there usually is, and we've seen that quite effectively. We found the most insane active regions that have ever existed, producing 60 flares on the disk. So, but yeah, that would be interesting, because if you are getting, something perfectly independent, then you're basically saying that the energy structure as it exists on the active region doesn't matter. So, which is insane from a physical point of view. So, but yeah, so this, I see where this is getting at, so.
I guess we could look at like conditioning on a large flare occurring, like have it, I don't know.
Yeah.
Something
Yeah.
like, yeah.
But
It's
if-
worth looking at.
The big business is,
We have to sign off. It is 3:45 here. I think we are going to get kicked out anyway, because something is happening at here, 4 o'clock, right?
no, it doesn't happen in here, I take it in my office.
Thank you for attending, everyone, and thank you for such great, insightful questions and discussion. I'm
was a lot of
glad
fun.
that this happens.
No, it's very useful.
Yes.
Very
And
useful.
please follow up if you want to send anything to me afterwards. I will happily take your input and any criticisms or thoughts. I appreciate it.
So it's just about to say, so it's a big business trying to predict when a flare is going to happen, or what likelihood of a flare to given energy.
Yeah.
So because when you're looking at, say, something that has, if you have a very high cadence observation, you have to stop down your field of view, that means that you just have to guess where you think it's gonna happen, like a day before it happens. So this is, I can see where something like this could be very useful if it comes into, say, the world of prediction. So.
It's something rocket people would like to learn.
Oh,
Right.
because Amy Weinberg.
Sign off here, so let people.
Okay, well, just check it.
So, thank you all again. So, I think the next meeting, CHASC meeting is probably in 2 weeks. We'll keep an eye on your emails.
It's nice to watch.